The research paper explores the heat propagation in liquid 3He, focusing on the deviation from the standard behavior in the Fermi liquid picture at very low temperatures. It is demonstrated that the thermal diffusivity of this quantum liquid is bounded by fundamental physical constants and observed in classical liquids, indicating the presence of collective excitations as carriers of heat. The authors propose that these excitations have a wave vector of 2 kF and a mean free path equal to the de Broglie thermal length, providing an additional conducting channel with a T1/2 temperature dependence, consistent with experimental observations. The Fermi liquid picture of thermal conductivity in cubed He is shown to have a narrow validity, as evidenced by the temperature dependence of thermal conductivity, kappa, and scattering time, teak, in Figure 1. Contrary to expectations from standard Fermi liquid theory, teak T² is never constant, and instead exhibits a non-constant behavior. This deviation has been attributed to spin fluctuations, but the authors argue that this correction is unlikely to play a significant role at the temperatures of interest. The authors compare the temperature dependence of teak with the Planckian time, tau p, and find that at zero pressure, teak becomes of the order of tau p at approximately 0.1 K, while at 3 megapascals, near the melting pressure, teak falls below tau p at approximately 0.043 K. This crossover is concomitant with the passage from the Fermi liquid, Fl, to the non-Fermi liquid, NFL, regions of the phase diagram, as shown in Figure 2b. The possibility of a Planckian bound on dissipation is a topic of ongoing debate in condensed matter physics. The authors investigate the temperature dependence of thermal diffusivity, 500th, which exhibits a minimum at both zero pressure and 3 megapascals, as shown in Figure 3a. This behavior is consistent with that of classical fluids, where thermal diffusivity shows a minimum at the intersection of liquid-like and gas-like regimes, as illustrated in Figure 3b for H and to the power of 4 He. The minimum thermal diffusivity, d-min, is found to have a similar amplitude in cubed He and other classical liquids, suggesting an important role for phonon-like collective excitations in heat transport. The authors propose that diffusion at high temperatures is driven by random particle motion, while at lower temperatures, collective excitations such as sound waves become dominant, leading to a minimum in thermal diffusivity. In the context of thermal conductivity in liquid cubed He, the authors delve into the scattering time, Planckian bound, and the Fermi liquid, Fl, to non-Fermi liquid, NFL, crossover. Figure 2a illustrates the fermion-fermion scattering time, teak, as a function of temperature for 2 molar volumes, alongside the Planckian time, tau p equals h, k underscore bt at high temperatures. Teak tends to fall below tau p. The phase diagram of cubed He in Figure 2b shows the fuzzy border between the Florida and NFL regimes, with temperatures below which teak greater than tau p or teak greater than 2 tau p marked. At high temperatures, the quasi-particle contribution to thermal conductivity becomes small, and collective excitations, specifically sound, become the primary carriers of heat. The collision time shorter than the Planckian time implies that the frequency of thermally excited zero sound is smaller than the scattering rate, placing the system in the hydrodynamic limit where the distinction between zero sound and first sound disappears. This occurs at a remarkably low temperature in liquid cubed He due to the short fermion-fermion scattering time. The authors analyze the temperature dependence of thermal conductivity, kappa, in normal liquid cubed He, citing Greywall's observation that kappa proportional T squared above 0.5 K. Figure 4a displays the temperature dependence of kappa, T, including Greywall's data and Murphy and Myers data, which roughly confirm the T squared tendency. This temperature dependence differs from phonon thermal conductivity in crystals and glasses, as well as the Bridgman formula for classical liquids. The authors introduce the quantum of thermal conductance, pi squared, 3k squared underscore b, and the transmission coefficient, T, set by the number of carrier modes and their mean free path. In 3 dimensions, the thermal conductivity is given by equation 1, kappa underscore T, qp equals 2 pi, 9k squared underscore bhk squared underscore fl underscore ff, where L underscore ff is the mean free path set by fermion-fermion scattering. At very low temperatures, the response to temperature gradients is dominated by quasi-particles, with kappa, T decreasing quadratically with temperature due to the temperature dependence of the mean free path of quasi-particles, L_QP. The authors aim to identify the collective transport mode leading to the T² temperature dependence dominant above 0.5 K by comparing it with other cases, including crystals, where phonons exhibit a cubic temperature dependence at low temperatures. Thermal diffusivity, a measure of heat propagation, is explored in various systems, including 3He, H2, and 4He. Figure 3 displays the thermal diffusivity of these systems as a function of temperature, showcasing distinct regimes. In the Fermi liquid regime, thermal diffusivity exhibits a T-2 dependence, followed by saturation and a minimum. In contrast, classical fluids, such as H2 and 4He, exhibit a T0 dependence. A comparative analysis of thermal conductivity mechanisms in different systems is presented in Table I, highlighting the distinct temperature dependencies of thermal conductivity in each regime. Crystals exhibit a T3 dependence, glasses a T2 dependence, classical liquids a T0 dependence, and quantum liquids like 3He a T1/2 dependence. The authors propose a novel mechanism for heat propagation in 3He, involving collective excitations with a wavevector fixed at twice the Fermi radius, Q equals 2 kilofarads. This scenario is supported by the Lindhardt function, which exhibits a singularity at Q equals 2 kilofarads, and inelastic X-ray scattering experiments that reveal an anomaly in the dispersion of zero sound near Q equals 2 kilofarads. The Landauer transmission rate of this heat-carrying mode is dependent on its mean free path, which is attenuated by the thermal fuzziness of the Fermi surface. The mean free path is quantified as lambda equals h square root 2 pi m asterisk operator kBt, where m asterisk operator is the effective mass. This mechanism enables the authors to circumvent the cubic temperature dependence of a Debye sphere, instead exhibiting a T1/2 dependence. The thermal conductivity of 3He at very low temperatures, specifically in the Fermi liquid regime, is a subject of significant interest. This page presents experimental data and a theoretical model that successfully describes the thermal conductivity as a sum of two terms, one proportional to T-2 and another to T-1/2. The model's parameters are derived from the effective mass and carrier density of 3He. The refined model demonstrates good agreement with experimental data, showing a maximum discrepancy of about 10%. This similarity is akin to the Bridgman formula for classical liquids, where timescales for randomness are comparable. In the context of Fermi liquids, it is crucial to consider two modes of conduction: collisions between quasi-particles and the breathing of the Fermi surface. The theoretical model's accuracy underscores the importance of understanding the interplay between these two modes of conduction. The proportionality of the thermal conductivity to T-2 and T-1/2 suggests a complex interdependence between temperature and the mechanisms of heat transfer in 3He at very low temperatures. This research contributes to a deeper understanding of the behavior of Fermi liquids under extreme conditions, shedding light on the intricate dynamics involved in their thermal conductivity. The findings could potentially have implications for future studies on quantum fluids and their applications in quantum computing and other technologies. The research paper discusses the conduction of heat in materials through two distinct channels: transmission by quasi-particles and transmission by collective response of the Fermi surface. Figure 5 illustrates these channels, showing the dominant transmission by quasi-particles at low temperatures, resulting in a transmission proportional to T-2, and the collective response's transmission, proportional to T-1/2. The collective response is explained as a viscoelastic competing interests. The paper cites various research works that have contributed to the understanding of this subject. The thermal conductivity of amorphous materials is discussed, focusing on the lower limit to the thermal conductivity of disordered crystals as proposed by Cahill et al. In 1992. The concept of diffusions, Lacans, and propagates is introduced, which are characterizations of atomic vibrations in amorphous silicon. The paper also explores the thermal conductivity of disordered crystals, highlighting the role of diffusions in limiting thermal conductivity. The authors provide additional context and insights into the non-Fermi liquid behavior of 3He through 2 supplementary notes. In the first note, they examine the role of spin fluctuations in explaining this behavior. While early attempts attributed non-Fermi liquid behavior to spin fluctuations, the authors argue that the exchange energy of spins, estimated to be between 0.002 K and 0.00085 K, is insufficient to explain the observed behavior over a temperature range of at least 2 orders of magnitude larger. Furthermore, nuclear magnetic relaxation measurements and specific heat measurements do not provide evidence for the role of spin fluctuations in heat transport above 0.1 K. In the second supplementary note, the authors explore the lower bounds on thermal diffusivity and viscosity in classical liquids. They present a universal theoretical lower bound of thermal diffusivity, alpha min, defined by the equation alpha min equals 1/4 pi square root m per meter, where m is the electron mass and m is the molecule mass. This lower bound corresponds to the minima observed in the experimental curves of thermal diffusivity and kinematic viscosity for various classical liquids, including 4He, N2, Ar, and CO2. The minimum is attributed to the dynamical crossover between the low-temperature liquid-like regime, where particles undergo oscillatory motion, and the high-temperature gas-like regime, where particles exhibit diffusive motion. In condensed matter physics, thermal diffusivity is a crucial transport coefficient that characterizes the rate of heat diffusion in a material. In the context of helium-3, the theoretical minimum value of thermal diffusivity can be evaluated by considering the phonon mean free path in the liquid-like regime or the particle mean free path in the gas-like regime. These regimes are determined by the interatomic separation and Debye vibration frequency, which set the length scales and energy scales for phonon-mediated and particle-mediated heat transport, respectively. Notably, this theoretical minimum of thermal diffusivity coincides with a minimum in kinematic viscosity, as evident from experimental data. This correlation underscores the importance of understanding the underlying mechanisms governing heat transport in helium-3. Furthermore, the discussion highlights the relevance of the Planckian bound, which represents a fundamental limit on the thermal diffusivity of any material. In helium-3, the unusually large fermion-fermion scattering rate leads to a dimensionless cross-section of fermion-fermion scattering, which in turn affects the thermal transport properties. The Landauer picture of thermal conductivity provides a framework for understanding the role of fundamental constants and length scales in setting the expected magnitude and temperature dependence of transport coefficients. This picture emphasizes the importance of phonon-mediated heat transport and the interplay between phonon and particle mean free paths in determining the thermal diffusivity of helium-3. The electrical and thermal conductivity of various materials are examined, with a focus on the Fermi surface and its relation to electrical conductivity. In two-dimensional systems, the Fermi surface is a closed curve, whereas in three-dimensional systems, it's a closed surface. The Drude formula is presented as an equivalent expression for electrical conductivity, providing an alternative method for calculating this property. Thermal conductivity is then explored, with the Sommerfeld value introduced as a fundamental concept. This value is used to calculate thermal conductance, which is essential for understanding heat transfer in various materials. The Bridgman formula is discussed, highlighting its application to classical liquids, glasses, and quantum liquids. Notably, the value of R varies significantly between substances, influencing the thermal conductivity of each material. Glasses are a specific area of interest, with their thermal conductivity examined through a model derived by Cahill, Watson, and Pohl. This model provides crucial insights into the thermal properties of glasses, which are essential for understanding their behavior under different conditions. By connecting these concepts to previous discussions, Key findings are highlighted, emphasizing the significance of electrical and thermal conductivity in materials science. The discussion on this page delves into the differences between classical and Fermi-Dirac distributions in the context of entropy production rates. It highlights how the time scale for entropy production is influenced by the sound velocity in classical systems and the Fermi velocity in Fermi-Dirac systems. The relevance of group velocity and its temperature dependence is also emphasized. The relationship between sound velocity and Fermi velocity is explored, particularly through the Landau parameters. This section provides insight into the quantum, classical crossover, where the thermal conductivity equation converges with the classical Bridgman formula.